Welcome to Precalculus Algebra and a video on sequences. So consider this list of numbers. The first number is 2, the second number is 5, the third number is 8, then 11 and 14. Do you see how we started with 2 and then added 3 to get 5? And then we added 3 to get 8, added 3 again to get 11, and so on? This little ... means continued. So this sequence of number, or this pattern of numbers, is what we call a sequence, or this collection of numbers rather. Let me go ahead and give you another example of a sequence here and see if you can find the pattern. So take, how about start with 32, and then 16, 8, 4, 2, 1, 1/2, and so on. Do you see the pattern? So every time I'm dividing by 2 to get the next, what we call term of the sequence. So a sequence, you can think of it informally as an infinite, because they're infinite terms, right? The little ... means it goes on forever. So an infinite list of ordered numbers. So a couple things about this. Let's write this first. So first of all, it's ordered numbers in the sense that this is the first number, that's the second, third, and so on. And it's a list, right? It's a collection of numbers, and there's usually some sort of pattern. So we're actually going to need a more formal definition of this because it's going to make some of the terminology easier to work with. So let's go ahead and give a more formal definition, but you pretty much know what a sequence is looking at these two. So definition, a more formal definition. A sequence is a function, so it's a function whose domain is the set of natural numbers. And the terms of the sequence, so to really that expression, the terms, is really important. The terms of the sequence are the values of the function. So for example, the first sequence that we have, which was 2, 5, 8, 11, and 14, right? And then ... So I listed the first 5 terms of the sequence. So a sequence is really a function, and a function has an input and an output. And what you're seeing when you look at a sequence are the outputs of the function. In other words, you plug in 1 and you get 2. You plug in 2 and you get 5. You plug in 3 and you get 8. So if the function is denoted using if we use function notation, you plug in 1, you get 2. You get that number. And then I'm using a to denote the function. You plug in the number 2 and you get 5. That's telling you that 5 is the second term of the sequence. What's the third term of the sequence? That would be 8. What's the fourth term? That would be 11. What's the fifth term? Well, I'm looking up here. The fifth term is 14. Okay, so all you see are these numbers, and they're the outputs of the function. Now, sometimes though, or often, we're going to be using this notation as well. We're going to be referencing the function and then which term of the sequence we're talking about. Now, rather than write an a with a big 1 right there, people do this to sort of shorthand that. People write this, a with a little sub 1, and likewise a sub 2, a sub 3, and so on. So that term right there, that's the first term of the sequence, right? It's when you plug in 1, you get 2. That would be a sub 2. There's the third term of the sequence, the fourth term of the sequence, and the terms of the sequence are always the output of the function, okay? You never see the underlying natural numbers except in this context. So let me just write that down for you, that a sub 1, that we call that the first term of the sequence. And it's the output of the function. And a sub 2 would be the second term of the sequence. And then when we write a sub n, that would be the nth term of the sequence. Now you might say, what do you mean n? Well, give me a number. 100, do you want the 100th term of the sequence? I denote that as a sub 100, or just a 100. Okay, let's see some examples of what we can do with sequences. So find the first 5 terms of the sequence given by this nth term. So they tell you, hey, here's what you do with n. an, the nth term, is 2n divided by n plus 1. So we want to first find the first 5 terms. So what would the first term be, a1? Well, you plug in 1 for n. So 1 goes here, and a 1 goes there and there. So it's going to be 2 times 1, because it's the first term, divided by 1 plus 1. And so we're looking at 2 over 2, or 1. Okay, so the first term is 1. What's the second term? Let's check it out. Plug in a 2 here, right? So it's going to be 2 times 2 divided by 2 plus 1. We're looking at 4 thirds. So the second term of the sequence is 4/3. The third term is going to be 2 times 3 divided by 3 plus 1. So we're looking at 6/4, which can be reduced, and we always want to reduce, to 3/2. The fourth term of the sequence is going to be 2 times 4 divided by 4 plus 1. So it's going to be 8/5. And finally, the fifth term of the sequence is going to be 2 times 5 divided by 5 plus 1. So we're looking at 10/6 or 5/3. Okay, so these are the first 5 terms. There's the first one, second, third, fourth, and fifth term of the sequence. Let's try another one similar to that. So find the first 5 terms of the recursively defined sequence. Okay, so a sequence that's defined recursively is one where the term, a given term, in some way depends upon preceding terms explicitly. In other words, I can see that the nth term explicitly depends upon the term n minus 1. And you can see the problem, right? It's like if the fifth term depends upon the fourth, and the fourth depends upon the third, and the third depends upon the second, and the second depends upon the first, well, what do you do with the first? It can't depend upon the 0th term because there is no 0th term. And that's why they also give us the first term. They tell us where to start. So the first term is going to be 1, and then we want to figure out what the next terms are going to be. That is, when n is 2, what do we get? Let's write this down. When n is 2, according to the formula, a sub 2 is 2 times, and we simply plug in a 2 for n. A 2 goes right there. So it's going to be a sub 2 take away 1, which is 1, plus 3. And so what you can see now is that a sub 2 depends upon a sub 1. But we have a sub 1, right? We have the first step, the first rung of the ladder. So we plug that in, and it's 2 times 1 plus 3. And so we're looking at 2 times 4, which is 8. So we found a sub 2. It's equal to 8. What about when n is 3? Well, according to the formula, a sub 3 is 2 times, okay, a sub 3 take away 1, which is 2, plus 3. So it's 2 times, where do you get a sub 2? Well, we just found a sub 2, right, in the previous step. So a sub 2, according to this, is equal to 8. So it's going to be 8 plus 3. So it's 2 times 11, or 22. And a sub 4, continuing in the same pattern, is 2 times a sub 3 plus 3. So we're looking at 2 times, we found a sub 3 in the previous step, times 22 plus 3. So it's going to be 2 times 25, or 50. And then finally, a sub 5 is going to be 2 times a sub 4 plus 3, or 2 times the a sub 4 we just found, which is 50, plus 3. So it's 2 times 53, or 106. So we found the first 5 terms. Here's the first one. It was given a sub 2, a sub 3, a sub 4, and a sub 5. Okay, now it turns out you can work backwards. So rather than be given the nth term, sometimes they give you a sequence and they want you to find a pattern. So let's go ahead and do a couple of examples like that. So they want us to find the nth term of the sequence and have 2 examples here. Here's the first one and here's the second one. Now remember, the terms of the sequence, you want them to depend upon n, right? And n is the natural numbers. So when I look at this, right, I see there's a numerator and a denominator. And the denominator is actually easier to work with than the denominator is easier to work with here in this case than the numerator. Why? Because look at the numbers 2, 4, 6, 8. So what do you do to the natural numbers, right? This has to correspond to n equals 1, n equals 2, n equals 3, n equals 4. I can see that if I multiply all the n's by 1, if I multiply the n's by 2, I get the denominators. So in other words, isn't 2 2 times 1? 4 is 2 times 2. 6 is 2 times 3. 8 is 2 times 4. So I can see right away that the denominator, that is for the nth term, the denominator is always going to be 2 times n. That is, when n is 1, I get 2. When n is 2, I get 4. When n is 3, I get 6, and so on. Now the numerator is a little trickier. 1, 3, 5, 7. It's almost 2n, right? It's just one less than that. So you can see that the numerators are always one less than the denominator. So the numerator is not quite 2n. It's 2n take away 1. Let's see if that works. So this is for n equals 3. When n equals 3, what do I get? Well, the numerator is going to be 2 times 3, which is 6, take away 1. That gives me my 5. And the denominator is 2 times 3, which is 6, and so it works. So this is going to be my answer. This is the nth term of the sequence. It's going to work for these 4, and then ... it'll work for any n you want. How about this next one? Well, the first thing I notice here is that these terms are alternating in sign, right? Negative, positive, negative, and so on. So this is called an alternating sequence. When we say alternating, we mean alternating in sign. It's understood that it's the sign that's alternating. So first thing I'm going to do to take care of when you have a sequence that's alternating in sign, or an alternating sequence, what you do is you first address the sign, and you take a -1 and you raise it to either n or n plus 1. You raise it to the nth term if you want the odd numbers to be negative. So here I want 1, 3, 5, right? The first term, the third term, and the fifth term, those are all negative. And so -1 to an odd power will retain the negativeness. But when n is even, that is the second term, the fourth term, the sixth term, those are all positive. So if n is an even number, when you raise -1 to the even number, it's going to be positive, which is what we want. So this -1 to the n takes care of both negative for odd terms and positive for even terms. And then the second issue, once you've addressed sign, is, well, what about just the numbers without the sign? Well, I can clearly see that I'm taking 2 and I'm raising it to the exponent, right? So this is 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, and so I write that in. It's 2 to the n. So this would be my answer because it takes care of both conditions. It takes care of the sign, so I can address that it's alternating, but then after the sign has been taken care of, it gives me the absolute value of the terms of the sequence. So this would be my answer. Okay, we'll have more to say about sequences in the future videos. Until next time.